Hi, I'm Shane Ardo. I'm a postdoc in the Lewis Group at Caltech, and I'm also a member of the Solar Army, as you can see from my shirt here. What I'm going to explain today is an extension to the dye-sensitized solar cell module that you did with your students already. So after taking the dye-sensitized solar cells, you've already shown that you can generate current and voltage from them when they're illuminated with sunlight. But as we all know, the sun goes down at night. So we'd like to do something with that transient current and voltage. And we think it would be interesting in the CCI and also in this extension here to store that transient energy in chemical bonds. And you did some of this already at one of the workshops in the water splitting demo, where you took electricity and you split water into its constituents of hydrogen and oxygen. So what I'm going to show you today is how you can take the dye-sensitized solar cells from your class. You can wire them together, which I'll explain why that is important in a second. And you can actually evolve hydrogen from sunlight using the dye-sensitized solar cells that your class made. So once you've measured the performance of the dye-sensitized solar cells with your class, you want to record the current and voltage for each one, as you've already seen. The reason you want to do that is because you want to find the best performing dye-sensitized solar cells. Now there's obviously two parameters here, both current and voltage, and ideally we'd like the largest of both. Okay, the voltage is going to depict how much energy or potential we have to drive the chemical reactions, which I'll show you in a moment. The current is proportional to the rate that you drive those reactions, so we want both things going on. I found it best when you choose the dye-sensitized solar cells that have the largest current, and you want to choose about 5 of them. So I'm going to go through the list here and take the 5 that have the largest current and select them. Now what I'm going to do is take these 5 cells and wire them together. Where before we would put alligator clips on either side of this, one to our dye-sensitized electrode and one to the counter electrode. What we're going to do now is hook one alligator clip to the dye-sensitized electrode and connect that to the counter electrode of another dye-sensitized solar cell. What we're doing is connecting these electrically in series. And what that means is the current's going to flow through both of these, but we're going to get an additive effect of the voltages. So we'll be able to have larger voltages by doing that. So I'm just using now a Tupperware top that comes in handy later if your overhead projector doesn't really get you a large enough light to drive these reactions fast enough. You can always lift these up higher on this top to focus the light and have a larger current. For now, I'm just going to put them here. I'm going to grab some alligator clips. Unfortunately, you're going to need extra alligator clips, at least 1 per dye-sensitized solar cell. So I'll attach one, like I said before, to the sensitized side of this electrode. You can see it just has 1 binder clip, but that's fine. It's held together and it functions. And I'm going to attach that over here now to the counter electrode of the next dye-sensitized solar cell. So each of these dye-sensitized solar cells outputs about 400 millivolts of potential. By hooking them up, again, we're adding the voltages. So right now, effectively, we'd have about 800 millivolts of potential. So if I take the next alligator clip and just continue this process, I'll attach this one again to the sensitized electrode and then connect it to another counter electrode. And now I have 3, which should be about 1.2 volts of potential. And I can continue this process, attaching to another dye-sensitized electrode and hooking that up to another counter electrode. I might have to adjust this a little. So a few pointers with this setup. I find it advantageous to have all of the cells very close to one another in the middle, and as when we measured these before, having the dye-sensitized side facing the light so that the most of the light can be absorbed and is not reflected by the counter electrode. Again, keeping these together in the middle so that if you want to, you can raise this up. Now we want to measure and see if indeed we have about 2 volts of potential, as you would expect. So now I'm going to hook up my multimeter into this circuit. Again, I have it on a voltage setting, and we often start at the smallest voltage and work our way up. So I'll take the alligator clips from the multimeter, and attach that to the remaining dye-sensitized electrode and the remaining counter electrode. So then I turn the digital multimeter on to see what the voltage is in the cell in the dark. And again, I'm on the lowest range, which is 200 millivolts. And since there's a -1, it means the dark voltage, the voltage just from room light essentially, is greater than 200 millivolts. So if I turn this up one setting, you'll see there's about 250 millivolts just from room light. Now when I turn the light on to the overhead projector, you'll see the voltage becomes much larger. Again, a -1 means it's too large for the range, and the range we're on right now is the 2 volt setting. So if I turn up to the next setting, you'll see we have over 2 volts of potential out of these 5 dye-sensitized solar cells.